Hi everyone, I am Jeng from InSpam. I am very grateful that I have been awarded the Excellence in Scholarly Publication 2020 by InSpam. The field that I have worked with is actually about mathematical finance, and I have actually prepared some slides for some of the highlights of my work that I have published in the year 2020. So here are the slides. So my supervisor is Professor Dr. Adam, and my co-supervisor is Associate Professor Dr. Siti. So chapter 1 is about introduction. My work actually revolves around pricing a particular derivative in financial market called option, which has the payoff of the maximum of stock price minus the strike price, or zero, where the ST is the stock price expiration date and K is the strike price. To do so, we actually need to model the stock price process as a stochastic process, and one of the components that would actually affect the stock price process is the volatility process or the variance process. So the volatility or variance process is actually very important in determining the value of option, as it determines whether the stock price might have larger or smaller deviation in movement. So here are some of the progress of volatility modeling. For several decades, the researchers have been trying to accurately model the volatility component without including too many parameters. For instance, local stochastic volatility models often have many parameters. So around 7 years ago, Kathy Rao and his co-authors have actually discovered that the log volatility behaves essentially like a fractional Brownian motion, and they have actually suggested that the volatility should be modeled as well. So their findings actually subsequently open up an entire branch of volatility modeling that uses the idea of fractional Brownian motion of the Heston parameters 0 to 0.5. The volatility component is now known as rough volatility. So there are many definitions of fractional Brownian motion. Equation number 1 is one of them. So it is actually defined in the Heston parameter range of 0 to 0.5 and 0.5 to 1. So when the Heston parameter h equals to 0.5, the fractional Brownian motion actually reverts back to the classical Brownian motion. Here we have 3 different figures of the fractional Brownian motion that uses the same set of path. But on the top left, we can actually see that it has very strong effect of the anti-persistency effect. And on the top right, we can actually see that there is positive correlated increments of the fractional Brownian motion, and on the bottom, this is actually the classical Brownian motion. So we know that the volatility should be modeled using fractional Brownian motion. What can we actually do about it? We can actually roughen up at the existing models to include the fractional components. So, for example, the first proposed models to price an option was actually a rough version of Bergomi model, now known as R-Bergomi. So after that, an interesting paper with the title of Microstructural Foundations of Leverage Effect and Rough Volatility have actually discovered that in the long run, their model, which is the microscopic Hawkins process, behaves essentially like a rough version of Heston model. So my work actually mainly focuses on the rough Heston model and the option price, which is in chapter 2. So equation number 3 is actually the rough Heston model, the variance process. Originally, this was a stochastic Boltzmann equation, but after some modification, it can be shortened down to equation number 3, where the CU is the power variance curve. So there are several features of the rough Heston model. The first one is that it has the mechanism that prevents statistical arbitrage. The second one is the liquidity as a metric function. The third one is it can mimic the high degree of endogeneity of the market. And as for the last one, it actually has it can actually replicate the effect such that a significant amount of trading transaction is part of the meta orders. So there are several methods to compute option price under the rough Heston model. We have 3 of them in this figure. So the first one is the Fourier inversion method, which uses the characteristic function. The second one is the approximation option pricing formula, which is we will discuss later. And the last one is the Monte Carlo solution. We will not talk about this in this presentation. So the characteristic function of the rough Heston model is actually been derived in equation number 3. So this is I is the imaginary number, A is the variable, XT is the log stock price, CTU is actually the following curve, D alpha H is the fractional Riccati equation, which is defined in equation number 5, where the H is the unique solution and D alpha is the operator of Riemann-Liouville fractional differentiation. So if we actually have the characteristic function, we can actually plug the characteristic function into equation number 6, which is the Lewis call option pricing formula. Then after an integration, we can actually obtain for the call option price. Okay. So the main problem is actually when we use the Fourier inversion method to price option under the rough Heston model, we actually require ON square multiplied by NS time complexity, where the N is the number of steps in the fraction Adams method, and the NS is the number of steps for the numerical integration of Lewis option pricing formula. So the main contributing factor is actually the presence of fractional Riccati equation, which needs to be solved at ON square by the fractional Adams method. And this problem has actually been reviewed by other authors, where the authors have proposed a method called paid approximant to approximate the fractional Riccati equation solution in O1 time complexity. But the authors have actually noted that this is not entirely accurate for the whole Hurst-Barrington range of 0 to 0.5. So to go around the problem, we can actually use two different methods. In chapter 4, we have the first method, which is the paid approximant. So the paid approximant is actually defined as rational approximation of polynomial equations. So for some specific reason, the terms on the numerator must be the same as the denominator. That's why we have a k-order paid approximation defined as equation number 7. So our main aim is actually to approximate the fractional Riccati equation solution H, which is defined in equation number 8. So to approximate the fractional Riccati equation solution, we actually need to solve for the Pj and Qj terms. So while we do not have the closed form solution for the fractional Riccati equation solution, we can actually use the short time and long time series expansion of the fractional Riccati equation solution in terms of infinity series expansion. So the infinity series expansion is actually defined as follows: equation 10 and 11 12. So the equation 11 is actually the short time expansion, whereas equation 12 is the long time expansion. So to solve for the Pj and Qj terms, we can actually match the terms such as in equation 13 and 14 when the time goes to 0 and time goes to infinity. So before that, we can actually propose a fourth order paid approximant, which has 3 different variants: 5, 4, 6, 3, and 7, 2, whenever the condition is fulfilled. So to solve for the Pj and Qj terms, we can actually define equation 16 and 17, which is the individual terms of the short time series expansion and long time expansion. So from equation 11 and 12. So we can actually solve for the Pj and Qj terms using this matrix. This is for the case of 5, 4, 6, 3, 7, 2. So the computational methods based on the paid approximation and the fractional Adams method is shown in this figure. So on the left side, we can actually see that fractional Adams method, if the fractional Adams method is used to solve the fractional Riccati equation, we actually need ON square multiplied by NS time complexity. Whereas if we use paid approximation method, we only need ONS time complexity. So the second method is actually about constructing an approximation for the option price under the rough Heston model by decomposing the option price under the stock and volatility dynamics. So the decomposition formula will be based on equation 21 and 22, which is the future expected variance and the martingale. So definition number 5 is actually the most famous option pricing formula, which is the Black-Scholes equation, defined as equation 23, so and denoted as P. So using the Black-Scholes option pricing formula, we can actually decompose several dynamics based on the volatility and stock dynamics in equation 25. So we have this as the decomposition formula. So based on assumption number 1, we can actually derive the approximation formula in equation 26, where the B is actually the Black-Scholes option pricing formula, H, U, K, and R are actually defined as follows: equation 27, 28, 29, and 30. So we can actually further extend the approximation formula by constructing a second-order implied volatility approximation by matching the Taylor expansion of the option price around the initial volatility. And interestingly, we can derive two limiting behavior about the implied volatility approximation. For example, the money term structure of implied volatility. So regarding the computational cost of the approximation formula, if we use flat forward variance curve in the computation, we only require O1 time complexity. Whereas if we use normal kind of forward variance curve, we require ONF time complexity. So chapter 6 talks about the contribution, significance, application, and future research on my work. So the main contribution is that I have formulated the fourth order total paid approximation that can accurately approximate fractional Riccati equation solution even at higher Heston parameter as compared to the previous study. And then we can actually compute for the option price under the rough Heston model through the forward inversion method. And the second main contribution is actually about constructing an approximation formula for the option price under the rough Heston model, where the error bound of the approximation formula has been provided in the work itself. So in addition, we can also derive the second order implied volatility approximation as its key short-term behavior, such as the money term structure implied volatility skew. We have also numerically tested the money term structure implied volatility skew against the original skew computed under the rough Heston model. So about the significance, we can actually now compute for the option price under the rough Heston model in ONS time complexity if we use fourth order paid approximation. And if we use the approximation formula, and it only require O1 time complexity or ONF time complexity, depending on the structure of the forward variance curve. For the third significance of my study, it is actually about the calibration of parameters of the model can actually be completed in a type efficient manner. If we actually use the fractional Adams method to solve the fractional Riccati equation, we would actually require many hours or even days to complete the calibration. Whereas for our methods, it will only take minutes to complete. So the application, we can now compute for the option price under the rough Heston model in an accurate manner and in a timely manner. So I believe there is also practical application in high frequency trading for my work. And as for the future research, the fractional Riccati equation actually present in many different fields, such as the batch reactor, rheology, fusion process, and so on. So I believe my work would actually contribute to their fields as well. So for the second future research, it is actually about the error bound of the approximation option pricing formula on the Heston parameter range of H0 to 0.1 is actually still not found yet. So the third future research is actually about the strong convergence of the stochastic total equation, which is a case of the rough Heston model, has actually not been found yet. Only the weak convergence has been proven. So these are the list of publications in 2020. So I hope everyone is well and stay safe, everyone. These are my references.